Okay, why don't we get started? This is lecture 9, and we are going to continue discussing health today, and I think we're going to wrap up health probably on Thursday, so we're probably going to go over a little bit. I don't think we're going to get through all the material today. If you haven't handed in your prom set by now, please don't. Just wait till the end of class to do so. If you haven't handed in your prom set by now, please wait till the end of class to do so. Thanks. Okay, it's due today. Hand in at the end of class from now on. Thanks. Any questions before we get started? Okay, I want to get back to estimating externalities within school externality impacts. And then we're going to talk about cross-school externality impacts, and we're going to actually turn to some of the other impacts of deworming. Please don't hand in your prompts until the end of class at this point. Thanks. Okay, clicker question. Let's just get going right away to get everybody's mind basically back in thinking about externalities and trying to understand the impact of a real-world, large-scale deworming program. So to best understand the effect of a real-world program, large-scale, real-world, big program, should we be focusing on the difference between the treated and the untreated within treatment schools, between the untreated in treatment schools and the untreated in comparison schools or control schools, or the treated in treatment schools versus the untreated in comparison schools? So please click in, or none of the above. Did I kind of give away that wasn't the right answer? Or none of the above. It's totally plausible. So let's just go through a minute here. I think most people already clicked in. Okay, 5 more seconds if you haven't. Okay, so what does it look like? Okay, so most of you picked C, which is what I was sort of going for, but it could be C or D, actually. We'll talk today about within-school externalities and cross-school externalities, and why D could actually be useful. And what I presented so far, C is sort of the right answer, but we're kind of getting towards why D might be the right answer. Okay, great. So we wrapped up last time talking about these within-school externalities. Here's the plot we had. We looked at infection rates in early 1999 when Group 1 had been receiving deworming for a year, and Group 2 had not yet started receiving deworming. And we compared the Group 1 folks treated versus untreated, 24% versus 34% infection rate, and we compared them to the control group 2, which was just about to start getting into deworming, and talked about how that difference between the treated and the untreated was so different, so much smaller than the difference between the treatment schools and the control schools, and how this is sort of prima facie evidence for some sort of within-school externality. There was a caveat we talked about, we went through a bit last time, which was treatment within the treatment schools was not randomly assigned. Certain people systematically chose to get treated, others chose not to get treated, so that's a limitation of interpreting these as within-school externalities, because maybe the people that got treated are just different. Maybe they were just healthier. But I presented some evidence last time showing that baseline health looked very similar between these two groups, and in the 2004 paper we showed that their observable characteristics look similar. So we discussed that. So there's no clear, selection on observables. That said, there could still be some limited variable bias in there. What I want to do next is talk about how we would estimate these within-school externalities, and sort of extend the estimation framework we've had so far to consider within-school externalities, and then we're going to extend the framework we have so far to consider cross-school externalities and talk about those different effects. So this is the equation we were kind of leading off with last time. We were just about getting here. Let's imagine regressing an outcome y, so some educational outcome, on the treatment dummy t. And again, this is assignment to a deworming school. So this is Group 1 has a t equals 1 in 98 because they were assigned to receive deworming. The indicator variable d is a dummy for actually taking the drugs. So not assigned to be taking it, but when we actually went and recorded who took the pills, d equals 1 if you actually took the deworming drugs. And we still have this child characteristic x, which may or may not be observed, let's just say. So this is just like what we had before. We had this new term of c times d, and I've highlighted in red the sort of assignment to deworming terms. So there are these two different treatment terms. One is assignment to treatment, and one is actual treatment, d. Any questions on the notation? If we want to put the estimates we have so far into this framework, b is the difference between assigned to t equals 0, assigned to a control school, versus being assigned to a treatment school, but not being treated yourself. And that's what b is. So that difference in this, so look at these simple summary stats, is 52% minus 34%. For the people who received the drugs themselves, they were actually treated. That's C, the term C in the equation. That's the difference between the treated and untreated in the treatment schools. So that's 10 percentage points. Let me just pause for a second. Does that make sense? Yeah, in the back. Yeah, exactly. So there's these two variables. There's T, and this could either be 1, so this is the treatment school. But among these people in the treatment schools, some have d equals 1. They were actually treated. They actually took the deworming pills. And some have d equals 0. They were untreated. And then the control schools are t equals 0. So this is the control schools. And almost nobody here took the treatment. Very small numbers of people went off on their own and got deworming drugs. So for simplicity here, let's just say d equals 0 for everybody. In reality, it's a few percent. Yeah. The coefficient estimate on t, so the equation looks like yi equals a plus bti plus z di. That's what the estimation equation looks like. Now, I'm a little bit casual with subscripts here. And what I mean by casual is, if we were estimating this at the individual level, we might change the subscripts. We might allow subscript I to denote the school, and we might denote, say, subscript J, another letter, to denote the person. And in that case, treatment assignment is done at the school level, but actual treatment is an individual level variable, d sub ij. So with this characteristic, so with the error term. So this is sort of a more careful way of writing it in some sense if you think about the level at which there's variation in T and D. Does that make sense? Okay. Any other questions or thoughts on this? So the folks who are both treated and in a treatment school, the difference between them and the control is b plus c, because t equals 1 and d equals 1. For the folks that did not get treatment themselves but were assigned to a treatment school, the difference between them and the control is B. What assumption am I making when I talk about those differences? This gets back to the caveat I just talked about before. What assumption on X am I implicitly making in this discussion? Yeah. Yeah, I'm basically assuming the way of the omitted variable problem, because it could be that some of the difference between the untreated and the treated is coming from differences in the X, because it wasn't randomly assigned. Now I showed you they look really balanced and blah, 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 but that's not strictly enough. So again, the within school externality estimates, because they're not based on the randomization, are always going to be a little bit more caveated and uncertain than what we're going to come to next. Okay, great. Sounds like folks are maybe getting it. This is another way to present this graphically. The difference between the infection level in the control group, which is 52%, down to the infection in the untreated in the treatment school, so that's benefiting from these externalities in the treatment schools, that's C. And then the further difference down to the 24% is B. Let's say, yeah.
So how the left side of the economy market that makes up the pool?
Yeah.
How does the magnitude of every compare to what you guys have? Because there's obviously
The studies weren't done in exactly the same setting. I'm trying to think of if I know sort of those numbers on the tips of my fingers. I'm not sure I do. Those studies did collect things like worm infection rates and worm loads and whatnot, so that we could compare. Those other studies did not collect the kind of educational data we collected. So we could compare them on worm loads. I do know that the estimates in those existing studies were smaller than our cluster randomized treatment versus control school estimates, but I don't know the exact comparison magnitude of our within school externality estimates. But what you're saying is a very good idea. If we believe that the settings were sort of comparable enough, we could get some sense about the omitted variable bias by comparing those estimates. So it's a very good idea. I don't have the numbers on my fingertips. Okay, so the naive treatment effect, and this is what I was talking about last time, would just compare treated and untreated in a treatment school, and that difference is B. It's the difference between the treated and untreated in a setting where lots of people are getting treated, so there's all these kind of externality effects. The actual treatment effect here, or something closer to the actual treatment effect, assuming these X's are not a problem, is B plus C. But B plus C isn't the only treatment effect. There's also all the externality benefits for the untreated. So the overall benefit of the program is B plus C for the treated, however many treated there are, plus C for however many untreated there are, if we think of this as sort of the numbers, the proportions. That's the sort of overall benefit. So by not considering externalities, we're doubly undercounting benefits. We're understating effects for the treated, and we're missing them entirely for the untreated. So that could potentially lead to a real misleading cost-benefit analysis, for instance. Are folks just sick of deworming after the problem set? I've been doing this for 15 years. I should be sick of it. Any comments or thoughts? Okay. Let's go to cross-school externalities. So we've talked about within-school externalities and this caveat of there being non-random selection into treatment. What we find, and I'll tell you how, when we look for cross-school externalities, is very large reductions in infection rates for schools that are located near treatment schools. So for instance, if you look at the group 2 schools that happen to be located near lots of group 1 schools in year 1, they have lower infection rates than the group 2 schools that just don't happen to be located near lots of group 1 schools. And that's further evidence of externalities. A lot of these effects happen at a pretty local area, like 3-kilometer radius, but we estimate some externality effects out to 6-kilometer radius, so about 4 miles away. So how do we do this, or how does it work? Consider the map. This is the map of schools before. I'm going to show you, I'm going to point arrows at 2 different schools. So the first one pointing out here is that, you see that 2 that the red arrow is pointing at? Consider that our group 2 school. And look at that circle in blue, which is roughly 3 kilometers, still less than 3 kilometers, around that school. And what do you see? Within that radius, there's actually a lot of schools. So in this part of Western Kenya, schools are very close together. Within a few kilometers, you will have a bunch of other schools. There's pretty dense population. There's 4 other schools in that circle, and a 5th one that's sort of partially in the circle. You can see 3 group 1 schools and 1 group 3 school. So 3/4 of the schools that are near that group 2 school were treated in 1998. So this is a school that just happens to be kind of surrounded by treatment schools. And remember, the assignment to these different groups was done through the list randomization. So the neighboring school could have been group 1, it could have been group 2, it could have been group 3, but by chance, these guys are surrounded by lots of group 1 schools. Contrast that group 2 school with a nearby group 2 school, not too far away, maybe, 8 or 10 kilometers away. That second group 2 school we pointed at. It also has 4 other schools around it, within a few kilometers, but all of those are control schools. None of them are group 1 schools. So that school isn't going to experience, if the theory about cross-school externalities is right, isn't going to experience the same sort of externalities that the other group 2 school will experience. So what we effectively do statistically is compare those 2 types of group 2 schools. Now, of course, there's a whole continuum. Some group 2 schools may have a small fraction of schools near them being group 1, a moderate fraction, a large fraction. We use all of that variation and figure out if infection levels are lower if you just happen to be located near more group 1 schools. Let me pause and see if that makes sense. Yeah. Yeah. That's a great question. And we look for this in the data. We look for externality effects not just on control schools, but also on treatment schools, and we find evidence for it as well. And in fact, when we, in general, try to compare the magnitude of the externalities experienced by the treatment schools and the control schools, they're very comparable. We typically can't reject that they have the same effect. So I've kind of illustrated it here with control schools because it's a little bit easier conceptually to make sense of. But group 1 schools would benefit from being near other group 1 schools too. And you might think, well, they were treated. How can they benefit more? They're going to benefit because they're not going to get reinfected as quickly. So the worms are going to be killed in their bodies, but if everybody else around them is getting treated, the reinfection rates are going to be much slower. That's the kind of theory, and that's what we find evidence for. So when I show you the estimation equation in a couple slides, we're going to be estimating these sorts of spillover effects for both treatment and control schools. That's a good question. Any other questions or thoughts on this map? Yeah. Yeah. Oh, I'm sorry. The question was, would the treatment schools themselves benefit from these externalities? Like within that blue circle, you see there's a bunch of group 1 schools near other group 1 schools, and we integrate the estimation of both groups. So sorry, I should repeat the question. Okay. So what do we find? We actually find a magnitude of cross-school externalities, the average effect, that's very similar, within those, say, 3 kilometers or even out to 6 kilometers, that's very similar to the within-school externality effect in terms of magnitude, roughly about 20 percentage points. Remember, the within-school externality was about 18 percentage points, something like that. So the within-school and cross-school externalities both look quite large. And this gets to the kind of clicker question and the sort of tricky nature of the clicker question, which is that none of the above is right. If even the control schools here are basically benefiting from being near treatment schools, then comparing people in treatment schools who are treated to the control schools may still not give us the full effect of the program if the control schools are benefiting too. And this cross-school externality approach is more attractive in some ways than the within-school externality approach because the assignment of schools to treatment groups is determined by the experiment, rather than individuals systematically selecting into getting treated or untreated. So that's the advantage of this kind of approach. And in subsequent RCTs, randomized controlled trials, a lot of authors use this kind of approach. They test for cross-school spillovers. They do a randomization, and they use the sort of raw variation in local treatment status induced by variation to estimate local spillover effects. That's something that's done a lot. Part of the reason why our paper is cited, or half the time this paper is cited, is because people are interested in the link between health and education. I'll show you the educational impacts next. The other half of the time, it's more for methodological reasons in using this kind of approach to estimate externalities of any program. So you could randomize a microcredit program across hundreds of villages and look for spillover effects across nearby villages. Spillover effects are plausible in microcredit because if I have access to a lot of credit, I can lend it to my neighbors in the next village. So you might actually expect there to be spillovers. And because of variation in local treatment intensity induced by randomization, some areas will have lots of villages with treatment and others won't. So it's a method that if you are interested in designing an impact evaluation, you could take advantage of if you're interested in the externalities. Now, if you really don't want the externalities, you really don't want this kind of contamination in the control group, then what you want to do is define groups of villages or individuals that are isolated from each other, far apart, clump them together to minimize those externalities. We did that to some extent by having a randomized cluster design at the school level, right? Because then at least the kids within a school are basically all assigned to treatment, and we don't have those kinds of spillovers. We have cross-school spillovers. If you're worried about cross-school spillovers, maybe you want to assign, you don't want to estimate them, then maybe you want to assign groups of schools to treatment, 3 or 4 nearby schools. Maybe if I go back to that figure and you see that there are these sort of collections of schools within the different circles, maybe you want to have clumps of schools all be treatment or control. That would be the way you minimize those spillovers. What would be the cost for the analysis of clumping schools together in these groups and randomizing treatment status in clumps rather than schools? Let's say clumps of 4. Yeah. So that's an interesting point, which is to say, if we think that one of the advantages of this approach is we have schools with different treatment status right nearby, so any flooding from Lake Victoria, any altitude effect or whatever kind of gets differenced out when we compare the group 1 and 2 schools that are next to each other in area. We lose that when we clump. That's one disadvantage of clumping. What's another one?
Reduce your available points analysis, so now clumping from the cluster schools rather than individual schools. So if you have 75 units that you randomize either by clumps, you only have like 20 or 30.
Exactly. So the other real clear disadvantage is sample size, and as you have a smaller and smaller sample size, you typically have less statistically precise estimates. So that's there's a bit of a trade-off, right? If we had gone down to the individual level, we would have had more precise estimates, smaller standard errors if we had randomized at the individual level. The downside would have been all of our estimates would have been contaminated by these spillovers. So there is some kind of, you can imagine coming up with optimal clumping or optimal clustering that limits contamination across treatment and control units to some extent while preserving statistical power. Yeah.
Why do you want to limit spillover effects? Are they as important as the quality?
So before I answer, maybe someone has an answer for that. There's a reason why you might not want to. But what might be a reason why you would want to limit these spillover effects? Yeah.
Well, the question you're trying to answer from perspective warning is not the spillover. So I guess you want to specify
Yes, we want so the reason why you might want to do is if you want an area or basically an individual school or a subregion that's like a pure control that isn't contaminated by these spillovers, and you want to compare that to an area where everybody all around you gets treated. That's kind of like the ideal experiment. What we really want to do is have a big enough sample so we could take 20 schools together, deworm all of them, get all the spillovers, cross school within school spillovers, and compare them to another clump of 20 schools where literally nobody got deworming. That would be like the pure treatment effect of a large scale program versus a pure control. And here the theory of what we're doing is 6 kilometers is a pretty big area. Very few schools have no treatment school within 6 kilometers. So everybody's probably getting a little spillover here. And so we don't have that much pure control. There's some isolated schools, and you can find these guys here are pretty far from group 1 schools or something. Yeah, in the back. Yeah. Yeah, so the spillover effects are very important to understand on their own. And this gets back to the point. You're saying they're important. They are important because the larger spillovers justify more subsidies because of the kind of standard public good rationale. They change the cost-benefit calculation potentially massively, et cetera. So we do want to understand them for sure. We may be interested in another treatment effect. So the other point here is we also really want to understand the difference between pure control and mass saturation with deworming to understand what the overall impact would be absent any contamination. Those are both interesting things. What we're able to do in this study is get at some of the spillovers and get close to some overall effect because we have schools that are relatively isolated. But we're not at the pure mass treatment, pure control level exactly. So maybe that was too convoluted, but yeah.
We're saying group 1 they're treated, so there's less infection, crossover, and transmission.
Yeah.
You also say groups 2 and 3 are actually hindering as well as groups they're cross-contaminating themselves.
That the groups 2 and 3 schools, you're saying the group 2 and 3 schools are cross-contaminating the other group 2 and 3 schools?
We'll say more often if they weren't here.
Definitely. I think that's really how we think about it. I'm going to show you an estimation equation that doesn't really deal with that directly. The estimation equation I'm going to talk about in a couple slides is a little different than what's in the paper. In the paper, the 2004 paper, oops, this turned off somehow. Sorry, let me just try to get it on in case people... Huh, there's no battery. Shit. But it's not recording. You see, it's okay. Don't tell me.